Hello everyone, I hope all of you will be doing well. In this video we are going to design a square square or reinforcement sheet column that is subjected to uniaxial bending moment using the interaction diagram. So a square column is given which have the dimensions of 16 inches by 16 inches with the material properties of f prime c equals to 4 ksi and fy equals to 60 ksi. And an applied load of 500 kips is also given along with the mx which is a bending moment along the x-axis is also given to be 120 kip feet. So we are going to use the interaction diagram for our design, and one thing that you need to remember that in practice we also use interaction diagram for designing the columns, because it is quite difficult or even impossible to every time develop separate interaction diagram for every cross section and one for different load combinations, load and moment combinations. So for simplicity and for doing the design easily, we use the interaction diagrams. So let me show you the interaction diagram. This is the interaction diagram that we are going to use. This is just a sample, because the interaction diagram depends on three different things: the concrete strength, the steel strength, and the gamma value that we will further see what it is. So based on these values, we are going to pick or select a specific interaction diagram, and then based on two factors, which is Kn and Rn, we are going to select steel ratio, reinforcement ratio for our column cross section. So let's start the designing procedure. We're going to design the column in a step-by-step manner. So the first step would be step number one. Step number one would be to determining the dimensions of column, the dimensions. So since the dimensions are given and we have d and d prime as well, we are going to skip this step. So dimensions are already given. Dimensions are given. So we are directly going to the second step. Step number two would be step number two. In step number two, we are going to determine the value of gamma. Determining the value of gamma. The value of gamma. You can note these steps and you will develop or you will design better using these steps. So in the second step, we are going to determine the value of gamma. So we have an equation for gamma. Gamma equals to h minus 2d prime divided upon h. It is the longer side of the cross section, and d prime is, as you know, the distance from the centroid of the steel reinforcement after the extreme fiber, either in tension or in compression. Since we are going to place the reinforcement in these two positions, the top and bottom layers, so this distance from the centroid to the extreme fiber is going to be used in here as d prime. So let me plug in the values. Since the column is a square column, so h equals to 16 inches. In this case, 16 minus 2 into 2.5 divided upon 16 again, and the value of gamma equals to 0.687. Let me highlight this value. We will need it further for our interaction diagram selection, and let me shift it upward. So now the third step would be to determine the two factors that we talked about earlier. Step number three would be calculating the Kn and Rn values. So let me show you the interaction diagram again, and let's focus on the equations in here. you can see Kn, that is in the y-axis, Kn equals to Pu upon phi f prime c into Ag. This is basically the total load, that is in this case 500 kips, divided upon the factored capacity of the concrete column. So in here the phi value would be 0.65 for f prime 60 and for f prime c for KSI. And because column is somewhat less ductile than beam, so we are getting a more conservative reduction factor for our design. And at the same time you can see Rn, which also equals to Pu into E. Now this term E, as you can see, E refers to the eccentricity, how much the load is applied away from the centroid of the column. If this is the centroid, E refers to the distance where the load is applied, and where the load applied from the centroid of the column. For example, if load is applied in this point, if load is applied at this point, if load is applied at this point, this distance refers to the E. This is the centroid and this is the point where the load is applied. So this is refers to E. Now basically, if we multiply this E into the given Pu or load, we will get this moment. See, so Pu into E is basically our Mx in this case. So the equation for Rn is mu divided upon phi f prime c Ag into H. Let's plug in the values and calculate the factors. So first we had Kn equals to Pu divided upon phi f prime of c into Ag, which equals to 500 divided upon 0.65 into 4 into 16 by 16. So Kn equals to 0.75. Let me highlight this as well, because we are going to need these factors in order to select our steel ratios. I will move this upward as well. So, and I will clear this space in order to have a space for our further writing. So we are still in our third step, so I'm gonna shift this upward as well. So now the value of Kn is determined to be 0.75. We are going to determine the value of Rn. Rn equals to Pu into E, as we said, equals to the given moment based on the eccentricity multiplied by the given load. So 120 multiplied into 12, we are converting it to inches because the numerator would be in inches. 0.65 multiplied into 4 multiplied into 16 by 16, and H was the longer side of the column by 16. So we get the value of Rn to be Rn equals to 0.14. So we have determined the three major factors for our steel percentage determination. So step number 4 would be, let me clean this writing in order to have a space. So step number 4, determine the steel percentage, the AS, which is based on rho, which is the steel percentage. So let's see the interaction diagram. So I have a gamma value of 0.687. Now what we do in practice, we interpolate this value based on the 0.7 graph and orientation diagram that has a lower gamma. So we interpolate it and determine the exact value of steel percentage for this. Now for simplicity and just to show how we are using the interaction diagram, we are going to use the closest interaction diagram to this value. So it is 0.7, and you can see the prime C, which is 4 ksi, and Fy equals to 60 ksi. We have got the two values, which are the Kn or n. Let's specify the points in the graph. We have the value of Rn to be 0.14. Since this is 0.15, so this is going to be 0.14. We are going to draw a straight line going upward from the point, and at the same time we have 0.75 as our Kn value. So this is 8 and this is 1, so this is going to be 6, and so in between these points you're going to have somewhat like in here. So we are going to draw a straight line. This is not straight. Somewhat close to this point because it is 0.75. So the point where they meet is exactly the point for our steel percentage. So it is likely to be something like 0.021%. So we determine the value of our steel percentage. Let me clean those lines. Rho equals to 0.021. So now multiplying, as we have AS equals to rho into AG. So AS in this case equals to 0.021 multiplied by 16 by 16. So our AS equals to, let me calculate the value of AS. So 0.021 multiplied by 16 by 16. So we have almost 5.4 inches, 5.38 square inch area. This is the steel area we just calculated. Let me shift this. So these were all the things we needed, and we only need to determine the number of bars right now. Number of bars equals to AS divided upon AB. Let's try. So equals to 5.38 divided upon AB. Let's assume to have number 8 bars. So number 8 basically have a 0.785 square inch area. So 5.38 divided upon 0.785, we are getting an odd number. So we are going to assume number 7 bar. 7 divided upon 8 multiplied with 0.875 multiplied into 3.14. So 5.38 divided upon 0.6. Again we are getting an even number, odd number. So let's assume number 9 this time. So number 9 has 1 square inch area. So if we divide 5.38 by 1, we are simply getting 5.38. So divided by 1 equals to 5.38. We will assume 6 inches. So the final answer would be to provide 6 number 9 bars. This is our final answer. So this is how we design our reinforced concrete column that is subjected to uniaxial bending moment, and in the case it is subjected to biaxial moment, which is the case for corner columns, we have another procedure that we convert the biaxial moment to a uniaxial moment, and then we do the same procedure that we did for this one. So in this video I just explained the procedure for designing a column, and I have not defined each step or each value or each factor separately. We will do that, and we will go through each of this in a separate video. Thank you very so much, and please subscribe the channel to have further videos.